Good day everyone, this is Jeremy Ramluchan and this is iTech 360. Welcome and I hope you enjoy, hope you learn something today. So today we'll be talking about asymmetric key cryptosystem fundamentals. I know that might sound like a bunch of jargon or it just might boggle you a little bit, but hopefully at the end of today's session we will all go away learning something. So let's get into it. I will be taking most of my material from the CISSP prep guide, so if you have that PDF for the book itself you can follow along, and so whatever diagrams or figures there are you would have a visual representation. I'll try my best to put some of those in here so that you could see, but yeah, well, that's pretty much it. Let's get into it. Now before I get into my particular topic, I just wanted to read the introduction of the chapter just so you all could further understand what we are going to be talking about today. So it says the purpose of cryptography is to protect transmitted information from being read and understood by anyone except the intended recipient. In the ideal sense, unauthorized individuals can never read an enciphered message. In practice, reading an enciphered communication can be a function of time. The effort and corresponding time which is required for an unauthorized individual to decipher an encrypted message may be so large that it can be impractical. By the time the message is decrypted, the information within the message may be of minimal value. Okay, so to make that even easier to understand, what that says is encrypted or enciphered data generally is difficult to crack, and 95% of the time trying to decipher said data is basically rendered futile because there is either one of two outcomes. It's either you decipher it and you get information where it is now no longer usable, or you just waste your time trying to decrypt and you fail. Right, so like I said, I will be talking about asymmetric key cryptosystems fundamentals, but if you want to know about the symmetric key cryptosystems fundamentals, you could check out our another video on the same channel done by Suvesh Sant, link in the description. Good, so with that out of the way, what is a asymmetric key, or what is asymmetric cryptography? This is a cryptographic system that uses a pair of keys, public keys which may be disseminated widely, and private keys which are known only to the user. And unlike secret key cryptosystems which make use of a single key that is known to a sender and receiver, public key systems employ two keys, a public key and a private key. The public key is made available to anyone wanting to encrypt and send a message. The private key, however, is used to decrypt the message. Thus, the need to exchange secret keys is eliminated, and I think I should mention that the public key cannot decrypt the message that it encrypted. Ideally, the private key cannot be derived from the public key, and a message that is decrypted by one of the keys can be decrypted by the other key. And well, obviously, the private key is kept private. Public key cryptography is possible through the application of a one-way function. A one-way function is a function that is easy to compute in one direction, yet it is difficult to compute in the reverse direction. Okay, take this function. If y equals 5 f of x, it would be easy to compute y if given x, yet it would be very difficult to derive x when given y. And if you still don't get it, listen to this. It is easy to find a number when given a name in a telephone directory, but it is difficult to find a name when given a number. For a one-way function to be useful in the context of public key cryptography, it should have a trapdoor. A trapdoor is a secret mechanism that enables you to easily accomplish the reverse function in a one-way function. So going back to our previous example, you can easily derive x when given y if you know the trapdoor. I must say that in the context of public key cryptography, it is very difficult to calculate the private key from the public key unless you know the trapdoor. Now, a number of public key algorithms have been developed Some of these algorithms are applicable to digital signatures, encryption, or both. Because there are more calculations associated with public key cryptography, it is 1,000 to 10,000 times slower than secret key cryptography. Thus, hybrid systems have evolved that use public key cryptography to safely distribute the secret keys used in symmetric key cryptography. Some of these important public key algorithms that have been developed include the DiffieHellman key exchange protocol, RSA, El-Gamal, Knapsack, and Elliptic Curve. So as I mentioned those, I'm going to just touch on them now, and we're going to start off with RSA. RSA is derived from the last names of its inventors, Revest, Shamir, and Edelman, however you pronounce it. A method for obtaining digital signatures and public key cryptosystems. This algorithm is based on the difficulty of factoring a number n, which is the product of two large prime numbers, and these numbers might be 200 digits each. This way, the difficulty in obtaining the private key from the public key is hard. One-way function that is equivalent to the difficulty of finding the prime factors of n. Now, the maths involved in this could be a little tricky, and talking about it without actually seeing it firsthand could confuse you all, so I'm not going into the maths of it. I also want to throw in there that RSA can be used for encryption, key exchange, and digital signatures. The DiffieHellman key exchange is a method where subjects exchange secret keys over a non-secure medium without exposing the keys. The method was disclosed by Dr. Whitfield Diffie and Martin Hellman in their seminal 1976 paper entitled New Directions in Cryptography. The method enables two users to exchange a secret key over an insecure medium without an additional session key. It has two system parameters, P and G. Both parameters are public and can be used by all the system's users. Parameter P is a prime number, and parameter G, which is usually called a generator, is an integer less than P. That has the following property: for every number in between 1 and P minus 1 inclusive, there is a power k of G, such that G to the power of k equals n mod. Alice and Bob can securely exchange a common secret key as follows, as you can see here. Alice can use a private value A and Bob can use a private value B. They put it together. Alice can now send to Bob and Bob can send to Alice, knowing her private value. Yes, and you can also see here after it is sent, you can see how the shared secret comes about. El-Gamal. Dr. T. El-Gamal extended the DiffieHellman concepts to apply to encryption and digital signatures. The El-Gamal system is non-patented, and it's a public key crypto system that is based on the discrete logarithm problem. It basically expanded on the DiffieHellman, adding a little more complexities to it, but it's basically the same. And like I said, the DiffieHellman key exchange is at the base of the El-Gamal system. The MerkelHellman knapsack, on the other hand, is based on the problem of having a set of items with fixed weights and determining which of these items can be added in order to obtain a given total weight. Now, this concept can be illustrated by using a super increasing set of weights. Super increasing meaning that each succeeding term in the set is greater than the sum of the previous. So the set 2, 3, 6, 12, 27, 52 has these properties. So that would be a super increasing set, right? If we have a knapsack with a total weight of 69, right, the problem would be to find the terms whose sum is equal to 69. The solution to this is simple. That is 52, 12, 3 and 2 would be in the knapsack, or equivalently, if we represent the terms that are in the knapsack by ones and those that are not by zeros, the ciphertext representing the plain text 69 is 110101. I want to throw in here that also the algorithm can be implemented faster than RSA, yet it was found insecure by AShamaluevMusic of RSA. Within the MerkelHellman knapsack, the keys are two knapsacks. The public key is a hard knapsack, knapsack A, and the private key is an easy, or like I said, super increasing knapsack B, combined with two additional numbers, a multiplier and a modulus. The multiplier and modulus can be used to convert the super increasing knapsack into the hard knapsack. These same numbers are used to transform the sum of the subset of the hard knapsack into the sum of the subset of the easy knapsack, which is a problem that is solvable in polynomial time. And finally, we come to the elliptic curve. Elliptic curves are another approach to public key cryptography. This method was developed independently by Neil Koblitz. So elliptic curves are usually defined over finite fields such as real and rational numbers, and implement an analog to the discrete logarithm problem. An elliptic curve is defined by the following equation: y squared equals x cubed plus ax plus b, along with a single point O, the point at infinity. The space of the elliptic curve has properties where addition is a counterpart of modular multiplication, and multiplication is the counterpart of modular exponentiation. So we are given 2 points, right, P and R, on an elliptic curve where P equals KR. Finding K is the hard problem, and this is what is known as the elliptic curve discrete logarithm problem. Because it is more difficult to compute elliptic curve discrete logarithms than conventional discrete logarithms, or to factor the product of large prime numbers, smaller key sizes in the elliptic curve implementation can yield higher levels of security. For example, an elliptic curve key of 160 bits is equivalent to a 1024-bit RSA key. This characteristic means fewer computational and memory requirements. Therefore, elliptical curve cryptography is suited to hardware applications such as smart cards and, well, wireless devices. Elliptic curves can be used to implement digital signatures, encryption, and key management capabilities. So you can see how versatile it is. Okay, and we have come to the end. I hope you have enjoyed. I hope you have learned something. Please leave your comments below, and I'll catch you next time.